Good morning and welcome to the second day of Google I/O. I hope you all enjoyed the party yesterday with Billy Idol. Yeah, from my youth. So we're going to talk about web programming languages and virtual machines. And we're trying to argue why it's important to always make it faster, so you guys can make better applications. I'm Lars, I'm the blue guy, and this is Kasper Lund.
I'm the red guy.
The red guy. And we are from Google, from the Danish engineering office. If you look tired, it's jet lag. All right. So just to know, so you know who we are, we've been working on virtual machines for too long. I started in '86. And in '86, working on virtual machines for object-oriented languages was sort of a little bit a niche. And it was only research communities that had an interest in it. But given today we have several hundred people here, I'm pleased that there's more interest for it. So I started working with Kasper 13 years ago, and we've been doing Java virtual machines, Smalltalk virtual machines, JavaScript virtual machines, and now Dart. So we sort of have a little bit of experience in doing compilers and garbage collectors. So hopefully we can tell you about some of our findings over the last many years. So why are we here? We are here because we truly believe that speed in web browsers fuel innovation for application developers, right? The more speed we can give you, the more interesting applications you can do. And we strongly believe in the fly-by web, right? Developers do one application, it runs on mobile phones and desktop systems, and this is just fantastic. And the source that makes that work is a virtual machine inside the browser. And if you can make it faster, you can take advantage of it. The question is, we have seen a lot of speed up in browsers over the last, I guess, 5 years. Is it fast enough, or do we want more speed? So we are of the opinion that we need to do even better. And that is one of the reasons why we have started on this new venture to do a Dart platform.
So before we dive into the technical details of virtual machines and programming for the web, I just wanted to take you back to 2006 when we started developing V8. At that point, web pages had evolved from being fairly static to being a little bit more rich. We were seeing sort of the first web applications appear. At the point in time, you were probably running Firefox 2.0, Internet Explorer 7.0, or some other browsers there. But it was very clear that these browsers were not really designed for long-running, heavy web applications. They were designed for the web of 2000, well, probably 2000, yeah. So it was an interesting point in time in 2006. It was just before we were seeing these applications really come to life on the web. And even if you look at the websites I've depicted up here, you can tell the difference if you can actually see it from the back of the room. That in 2008, already then we were seeing pages like BBC becoming a little bit more interactive and more rich. So in 2006, when we set out to implement a new virtual machine for JavaScript for the web, people believed that browsers were essentially fast enough. Web applications like Gmail and Google Maps ran fine, and people were very impressed with them. People also believed that JavaScript is just inherently too slow for writing heavy client-side computations. And even so, people didn't really expect the JavaScript to improve that much, so they didn't think that the execution of JavaScript was holding things back. They were okay with having more code running on the server side and having fairly limited amounts of logic on the client side. Another key thing for us when we started was that performance at that point was evaluated using very simple micro-benchmarks, where all the emphasis was put on simple loops with very simple arithmetic. Nobody paid any attention to the overhead for calling methods or how large applications would perform when it comes to memory management. So people were really spending all their time looking at small, simple loops and trying to make them run a little bit faster. So here's an example of a benchmark that I think represents that line of thought pretty well. This is a benchmark, a JavaScript benchmark from the SunSpider benchmark collection. It's known as bitwise-and, and that's all it does. It computes the bitwise-and of a series of values here, starting out with a fairly large number, and then it runs through a loop. And you'll probably notice that even on the first iteration, I is 0. So when you AND that with anything, you'll get 0 out. So this is just a fancy way of computing 0. Not exactly something you want to spend a lot of time on optimizing for, I guess. And it's certainly not something that would, if you actually did optimize this, it would turn your application any faster. So SunSpider is a benchmark that sort of represents some of the things and some of the problems from sort of the earlier web. And it is being updated every now and then, but not with any significant differences. This is from SunSpider 1.0, released a couple of weeks ago. It's very nice to see that I've added testing that actually does compute 0, but it's still a really bad benchmark. Making this faster and tuning V8 for these kind of things would not make your applications run any faster. So when we started designing V8, we had to make a choice. Like, what do we want to optimize for? And there are basically two approaches. You can optimize for the current apps and the current benchmarks. And that's a nice and simple incremental approach. And there's a good chance you can make things 10%, maybe 20% faster that way. We chose to optimize for the apps of the future at that point. So we decided that we wanted to support much heavier client-side computations. And we wanted to turn the browser into a scalable application platform, sort of thus enabling a new class of web apps that could be written. So optimizing a brand new virtual machine for some applications that you cannot write, or you couldn't write in 2006, required us to come up with some benchmarks and some metrics that would allow us to make progress on that problem, which is where the V8 benchmark suite entered the game. So the V8 benchmark suite is a collection of benchmarks that are structured and mostly object-oriented. And they're designed to push the limits of browsers in 2006, but also today. And it's benchmarks that are mostly proven valuable in the context of lots of other languages. So it's benchmarks that we know that if we optimize for those, it will actually make it possible for you guys to write much larger and much more interesting applications. It measures the performance of dynamic method calls and property access. And it also measures the performance of the memory management system, closure creation, invocation, to a much higher degree than any of the existing benchmarks in 2006.
But Kasper, can I get the mic? Thank you. Let's try to run it so we can see how it looks. So here I just searched for the V8 benchmark suite, and we can run version 7 of it. And you'll start running, and you'll see the results trickling in on the right-hand side, and you can see the collection of benchmarks we're running. It's 8 different benchmarks. They're not big, but they are certainly not micro benchmarks. And we should soon have the results. The interesting part is that the score you'll see is computed as the geometric mean between the individual scores, but it's calibrated for Firefox 2 on a high-end desktop machine in 2008. So we are pretty much running 160 times faster than one of the browsers in 2008. So this is pretty amazing.
Yeah, the score was 100 on Firefox 2 on my beefy desktop machine in 2008. It's a little bit better now, which is nice. So I think it's fair to conclude that the performance improvements for JavaScript over the last 8 years have been pretty impressive. JavaScript itself executes 100 times faster than it did before, at least. And we see people being able to write applications that use way bigger object heaps, and the GC pauses are even lower than they were at that point. Another key thing for us as compiler and VM engineers is that people pay attention now to performance of web apps. And it's very, very common to see benchmark numbers reported in the press. So there's a nice friendly competition going on to improve the web platform performance. Another thing that's very nice to see is that it's possible to write really large web apps these days. We see common pages like Amazon, CNN, and ESPN they're serving fairly large amounts of JavaScript code to their customers all day. So it's not uncommon to see like a megabyte of JavaScript code, minified JavaScript code being sent to clients. And the browsers are generally capable of working with that. So things have certainly changed since 2006. One thing that it's important for us is to pay attention to where the time is actually spent in your browser. And what you have here is a couple of diagrams that show that we're spending a around 60% of the time in JavaScript execution when you're running things like Gmail, Google Docs, Google Search, and things like that. And the rest is spent in the general browser infrastructure. On other sites like Twitter and Facebook, the percentage in JavaScript is a little bit lower than that. These measurements are all done by the Chrome team using Chrome, so we don't have the exact same numbers for the other browsers. But it shows that no matter how fast we make the engines, the application developers will adapt to that and add new functionality and essentially make their applications better by using this thing. So imagine how it would feel like running modern Gmail on a browser from 2006. I don't think you would like that at all. So today, web developers are really pushing the limits of the platform, and they really want and demand predictable high performance, higher and higher actually. They want consistent frame rates for their games, and they really want to support large-scale application development. So people's expectations for this platform have really changed. They really demand these things now, and all it took was a 100x performance improvement. It makes really, really a big change to the technology stack when you do these things. So the question is, of course, are the web developers getting predictable and high performance? And can they actually support really large-scale application development on the current web stack? So before we answer that question, I think we should dive into the current web stack and take a look at how we can improve the parts.
All right, now we'll dive into what actually happens inside the virtual machine in the browser. So I'll be talking about a few different techniques we've been using to make V8 fast, and I'll talk about the history behind these technologies. First let's look at a browser. So a browser has several parts, but if you look at the performance critical part for an web app, it actually consists of two segments. At the lower part, we have the JavaScript engine, where you have all the code and the objects and the wrap objects that points to the DOM. The DOM consists of the nodes that you can see on the screen. And when you execute your web application, you manipulate the DOM by executing JavaScript. We all hope that when you develop a web application, you have low latency, so it comes up fast and there's no pauses. It has high performance, and it also has low memory usage, so you don't end up swapping when you run the application. And then, of course, small pauses if you do animation. But there's still big fears when you run a web application, right? If the object heap is too big, you can get very large DC pauses, and you can have a memory leak. So having a web application that runs for weeks and suddenly it runs out of memory is not very pleasant for the user. And sometimes you get erratic performance behavior for no good reasons. And this is sort of some of the issues people are concerned about when writing for the web. Here's my picture of how a virtual machine or a JavaScript engine looked like in the year 2006. It had a simple parser that would take the source code and convert into an abstract syntax tree or into bytecodes. And then we'll have a simplistic interpreter that will run over the AST, abstract syntax tree, or the bytecodes and execute your program. And then we'll have a simple memory management system to clean out unused memory. Now, in 2006, you would not create many objects because you knew that if you create a lot of objects, your program would be slow. So you actually didn't use many of the object-oriented qualities of the system. So the conclusion is, it was very simple, and that's nice that you can write this kind of VM in a few thousand lines, but the downside was it was really slow. Today, we have a sports car, and I can guarantee you we have put in all kinds of fancy turbo engines in it to make it fast. Right? We still have a parser, but instead of an interpreter, we have a multi-tier adaptive compilation system. It's basically a series of compilers that learns from the behavior of the program and tries to optimize the execution based on behavior. We have a de-optimization system that allows the system to back out of optimization if the behavior of the program changes over time. And then we have a system that handles large object heaps. And in the V8 case, we have a generation-based garbage collector that allows us to have heaps up to 1 gigabyte at least, where you can still have reasonable pauses when running your program. Native code is generated on the fly and is generated by the buckets, I guarantee you. And what will happen when it's not used anymore, it will be removed by the garbage collector. So even return addresses on the execution stack will function like pointers into the code, and if they are not used anymore, code will be eliminated. And then, of course, there's all this tool support with debugging and profiling, because when you do optimizations, right, you sort of lose the understanding of what the source code is doing. So you cannot single step in optimized code. It will give no meaning to you. So what we try to do is we try to optimize the code if you try to single step, and it will look like you do single stepping in the normal source code. And that's great for a programmer, because then you can debug on an ARM-based system or an Intel-based system and get exactly the same behavior. It's really complex, but the good thing is it's fast. Let's go beyond the hood and see what's going on inside the V8 engine when it comes to a few things. I'll briefly mention how we make the code really fast, and this is this multi-tier adaptive compilation system. I'll talk about how we handle large object heaps by doing this generation-based garbage collection with a twist. And then I'll talk about how we bind JavaScript objects to the DOM nodes. And this is tricky, so I'm calling it the tangoing between the tracing DC and reference counting. So listen up, this might be a little bit tricky here. When you pass the code is blue. You have a sea of JavaScript methods. Nothing has been executed yet. When you start executing, the first simplistic compiler will take the source code and convert it into native code, right? It doesn't know much about the behavior of the program, so what it's doing is putting in inline cache stops that tracks the behavior of the program. So in essence, what it's doing at one call site in your program, it tries to figure out exactly what kind of type of objects comes by. At the same time, we have this monitoring system in the system that detects when a method is used frequently. If it's used frequently, we said, well, let's try to optimize it even further. And the optimizing native compiler, what it will do, it will take the collected type information from the inline caches and use that to do aggressive inlining. So it will basically assume that the behavior of the program you had before you optimize will be the same in all future. It's not always the case, but we're optimistic here. So we do these aggressive inlining decisions, but we put in the optimization hook so that if our assumptions are wrong in the optimized code, we can go back again to the naive, simple code. In most cases, we don't have to do that, and you get the predictable performance, which is great. It gets even harder, right? Because as you all know, there's no types in JavaScript, and that means we have to do funky stuff. One funky thing we are doing is that if you use an array and you put doubles in it, at some point at runtime we decide to optimize it by converting the representation of an object from an array that can have any kind of objects to a representation that can only have double values. Right. So we assume that moving forward, you will only operate on double values in this array. That will certainly speed up programs that continue to have that behavior, but you still need the hooks. If some from the side will put in an integer, or not an integer, let's say a string in that array, then we have to back out of that optimization and go back to the standard representation of an object array. Very complicated. But anyways, you will have a system that's always changing when you run it. Did we invent this multi-tier adaptive compilation? No, we are not that smart. There's actually a long history of implementing dynamic languages. Started with interpretation in the 50s with Lisp. In the 70s, we have dynamic compilation being added to Smalltalk. And they even had inline caching. It was not at the call side, but they put it at the callee. So instead of having it, the method calling it, it was actually at the prologue of the method you called. And then that adaptive compilation was invented in the 90s in the Self project, where you had mixed mode execution, runtime type feedback, and all this kind of stuff. And then they also came up with de-optimization. So let me try to explain what de-optimization is. It's actually very simple. When you have the optimized code and you have activations on the stack that's executing and you figure out that something is wrong, you need to revert. What you do is you take that optimized activation and convert it into a series of unoptimized activation on the stack, flush the optimized code, and start using the simple code again. So this first appeared commercially in the hotspot JVM. I assume you all know about what that is. The only thing we did in V8 to basically use all this technology was introducing behind-the-scenes classes. You know that JavaScript is prototype-based, but we faked them behind the scenes and event classes. Then you can apply all this technology that's on the slide, and that made it fast. The garbage collector in V8 is here. It might look complicated, but we have basically 2 generations. And the way it works is, as you are allocating objects in your program, we'll fill up the allocation space. It's called from here. When it's full, we'll start a garbage collection process. And we have a tracing garbage collector. That means that we have well-defined routes, and we start following these routes through the objects, through its references, until we have computed the complete live object graph. And memory that's not occupied by the live object graph, it's garbage, and it can be reclaimed and used for further objects. So let's see what happens when you do a new space collection in V8. We migrate the objects to the 2 space, and you can see it's smaller, and that is because most objects die young, and this is great. And then we can start allocating and filling up the 2 space and repeat the same story. The garbage collector in V8 is a precise garbage collector. It stops the world and processes the garbage and then continues on. You can see you have red pointers in the graph. It denotes that the system has a store buffer that tracks pointers from old generation to new generation. And you need that if you want to do fast new space garbage collection. You don't want to scan the whole heap in order to do a small garbage collection. The old space in V8 has been segmented into normal objects. That's the objects that's promoted from new space when they've survived for a while. And then native code, where you have native instructions. And then a segment where you have atomic data. Atomic data is data that does not have pointers out again. So it could be typed arrays or double objects, or something like that. They're just easier to handle in a separate space because they don't have pointers out. Anyways, we didn't invent that either, sorry. There's a long history of automatic memory management done in Lisp in the 50s. Incremental garbage collection done in 70s in Lisp as well. And then you have generation-based garbage collection that got invented by Dave Unger in the 80s, or generation-based scavenge and its use of Smalltalk. So all these techniques for doing garbage collection is fairly simple in my mind, because you have all the pointers to the objects and you can just process them. The hard part is actually dancing with the DOM. And I'll try to tell you how that works. So nodes in DOM is governed by what we call reference counting. And reference counting is a simplistic garbage collection technology that keeps a pointer in each object that tells how many pointers point to it. And that when that pointer goes to 0, you can deallocate the object. The problem is you don't know who points to it. You just know how many. That means that if you want to move the object memory, you cannot do that because you cannot find who point to it. And another deficiency of that mechanism is also if you have a cycle, which can happen, then it's a memory leak, because you will never get down to 0 in the reference count. And the problem is JavaScript V8 has objects that are traced, and we have to get all this to work. So here we go. Bear with me. This is complicated. On the top, you see the DOM. You have 2 nodes. The first node has a reference count of 1. The second one has a count of 2. And you have wrapper objects that point to these DOM nodes from beneath, and that is the V8 heap. Now, in order to make sure you can collect these objects, you have to make tricks. And you can see you have this pairing between JavaScript objects and DOM nodes by using weak pointers. So in essence, you have a JavaScript wrapper that points to a DOM node that in turn points to a persistent handle, that's the black ones, that in turn will use a weak pointer pointing back. So it's sort of a semi-cycle, and you break the cycle by using weak pointers. So that was simple. But it gets even more complicated. When V8 is running out of memory and has to perform a garbage collection, it has to call the DOM and ask the DOM to group all objects that belong together, because that's needed in order to only collect, or you basically have to collect all grouped objects at the same time. That's needed to avoid resurrection of wrapper objects. And that might seem complicated, but it's needed because if you add a property to one of the JavaScript nodes at the bottom, and it suddenly disappears and reappears again, the property is gone, and the application will get a little bit confused. So we need to do all this in order to make sure garbage collection works. Did we invent this? Actually, that's the only thing we did. And it works. Chrome is great. But that part we're not proud of. And it needs a lot more work in order to make sure that we can guarantee that all memory is collected the right way. But we'll get back to this later in this talk, what we're doing about it. So does this mean that V8 is as good as it gets? Right? We have taken all these techniques from the past, advanced compilation techniques with hidden classes and sophisticated memory management. Is this what we have, or do we want more performance? Well, from the feedback we're getting, there still are a lot of bottlenecks in the browser. Performance is not still at par with real languages. And you can define what real is your own way, but I would sort of at least say Java and C# as contenders. Performance is still unpredictable. And you can see if you do animation in a browser, sometimes you skip frames. And part of it is because you do too much compilation. Part of it is because you do garbage collections. Part of it is because you de-optimize because suddenly the assumption changed in the program. And in JavaScript, that's very easy to do because just jam in another property on a hot object, bam, performance changes. Startup is still slow. And the reason for that is that you still have to read in the source code whenever you have to start up the program. And of course, JavaScript is still JavaScript. There's a lot of implicit conversions of values when you run JavaScript. It's just complicated. So having said that, the V8 project is still doing excellent. They're still improving performance quarter after quarter. But we think that if you really want to push the performance to the next level, something else is needed. Let's look at performance over time when it comes to V8. This is a graph that shows the V8 benchmark score from the different versions of Chrome all the way up to today. And it's gone from 3,800 all the way up to 14,000. So it certainly has improved a lot. So this is great, but that's the downside. Here's the complexity over time of V8. And we measure complexity by number of lines of code in the VM. When we came out with V8, it was roughly 100,000 lines of code. Now it's 500,000 lines of code. And I don't know, as a programmer, you know that it's trouble when it gets so big. It takes way more effort in order to improve performance. So we question whether it's possible to get a factor of 2 in V8 in the near time. You can follow the graph. Factor of 2 will take a long time, unless it's rewritten, of course. which is also would be a fun project.
So we've gone through a lot of web technology stuff here and looked into how V8 works and why it's as fast as it is. Let's dive into the Dart side and look at how Dart improves this. So Dart is a simple, class-based, unsurprising programming language. It's designed to be very familiar so that web developers and application developers can pick it up and learn to use it in no time. We've got excellent feedback from users of the system that this really works. You can sit down and code in Dart, and within a few hours, you feel like you're very productive, and it actually works out really well. To hit that target of being very familiar, we've designed it based on principles and concepts found in other languages. So the syntax is very much inspired by JavaScript, Java, C#, those kind of languages. And we get a lot of other value from essentially standing on the shoulders of other good programming languages out there and picking the things that we feel like are good fits for a language that needs to be really efficient and at the same time very productive. One thing that we've added to Dart, which is a little bit uncommon, is support for optional static types. That means that you can write static type annotations where you want them, where you feel like they convey the intent that you want to convey, but you don't have to put them in. The system is very flexible that way. It doesn't require you, and it is a fully dynamically typed system. So it's hard to describe this in one slide without showing some code, so I'll use two. Here it is, a little bit of a taste of Dart. I don't know how many of you are familiar with Dart, tried it out, but for those of you who are seeing it for the first time, I hope you'll find this is reasonably readable. It's a very simple example that shows that all Dart applications start with a main function, and in this case I just added a little bit of a HTML interaction here, creating a new button element, adding that to the document body, and giving it a bit of text. Hopefully you can read this code if you're familiar with JavaScript, C#, Java, those kind of languages, and it doesn't feel too foreign for you. That's exactly what we wanted to try to get at. One thing that might look a little bit different here is the import, and it just shows that Dart has support for modularity. So you can import libraries of functionality and code and use that. So we do have a sort of a namespacing mechanism and a way of carving up your application in multiple independent bits. So I hope this seems reasonably easy to read for you guys. So I think a good question to ask at this point is, what are we trying to achieve with Dart? We feel that there is a need for a much more scalable development platform for web apps. We feel like it's too costly and too difficult to write great web apps. You can achieve amazing things on the web today, but you really have to invest a lot of time in it. Things are getting better, but we feel like we need something like Dart to push the limits of this and make it much, much easier to write large, well-functioning applications. We think there's a real need for higher performance and much faster startup. And we certainly feel like having predictable performance where it's harder to write applications that really perform poorly because of somewhat weird semantics in the core of the system that you're building on is a must. Another thing that we consistently hear from users of Dart and other systems is that having great toolability, being able to write tools and use tools on your code bases for refactoring, editing, and just maneuvering around, navigating your code is a great big help. And the static types that we have, even though they're optional, they're a big help here to just document your intent of your code and make use of it. Finally, I think it's very important for us that we make it easy and nice to use a set of consistent libraries and make it easy for the community to create new libraries and share them in a sane way. Certainly an area where the web has suffered a little bit. We see great things out there written for JavaScript, but it's not necessarily trivial to make things fit together if you have multiple independent pieces of JavaScript functionality you want to bring together. We're trying to make that better with Dart, so that's what we're trying to achieve. Clearly, we want Dart to be useful in all browsers, all modern browsers. So we've written a translator that translates Dart code to JavaScript that runs in all modern browsers. That translator in itself is actually written in Dart, so we are trying to dog food our own product here. And that's been a great experience for us to write a fairly significant amount of code in Dart, translate, and a translator that translates Dart to JavaScript can actually translate itself. So you can take that big piece of code and translate it to JavaScript, and then you have a Dart to JavaScript translator in JavaScript. That's kind of neat. So it runs across all modern browsers, and that's a big win here. So The users that actually try using Dart are fairly happy with some of the decisions we've made. And Thomas from an Austrian startup, Blossom, describes this fairly accurate in one of his quotes here. And he says that Dart is exactly what he needs to be productive on the web. So the feedback that we're getting on the productivity gains of using something like Dart for your web applications is very, very positive. I'll let this slide stay there for 2 more seconds so you can read it.
All right. Well, for me, it's good just to have a choice of another system if it fits your needs better. But let's go a little bit deeper when it comes to performance. I'd like to talk about why we can make Dart faster than JavaScript, or in some cases it already is. Right, we are VM engineers. We've done that for most of our professional lives. And we designed Dart to make sure we could optimize it. Maybe it's a little bit selfish, but it's basically so you can get better performance. So the language model, the language semantic, is very simple in Dart. It has a much simpler object model. That means that, right, when you first have allocated an object with fields, you cannot change it after allocation point. Right, that's it. And that allows us to have much faster access to fields, right? Just like in C# or in Java, you can actually access the nth element because you know that that is exactly where the foo property is. Programmers are declared, so you don't have to run Dart in order to set up the program, in contrast to JavaScript. That allows us to use snapshots for having fast startup of applications. We really like that feature. And then we just have fewer special corner cases to worry about. As an example of a corner case in JavaScript is that, well, you might actually like it as a programmer, that you can call a method with too many parameters or too few. Well, this is sort of nice, but in the implementation, right, somebody has to figure out what you called it with, and that costs, right? And if you don't provide enough arguments, somebody has to provide them for you, the underlying system. And stuff like that makes the code more complicated to generate, and the resulting code is also more bloated. Let's give an example. Here I've tried to make a side-by-side comparison between Dart and JavaScript and what code it generates and how it works. On the right side, you can see that we have 2 classes. We have a class A. It has a method called foo. It prints out foo. And then we have a subclass B that inherits from or extends A. It has nothing. And then you create a new B. It's called B, lowercase b. And the main function on the right, you call foo. Very, very simple. We try to mimic the same in JavaScript. You have to go to the left of the screen. The way we model inheritance in JavaScript is by using prototypes. So we make a function A, and in the prototype of A, we put in the foo function, just like on the right. And then we make a function B that calls the constructor of A. And in the B prototype, we don't do anything. We just set it to a new A. And then we create a new B, and we call B. So it's sort of the same, no difference. The problem in JavaScript when it comes to speed is you can actually, on the fly, change the code. So inside the box, you can see that right there, we're actually extending the B prototype with a new foo that prints new foo, and then you can call B foo again. And the semantics is you have to print out new foo now. So we don't have that in Dart, and we actually think it's a plus. It's certainly a plus for the implementation. So let's look at it. B is the object we created. That's the object we want to execute foo on. It points to the B prototype in JavaScript. That again points to the A prototype. When you start running the program, you don't have the middle foo, so you have to execute the one up in A. The problem is that you don't know if somebody is going to insert a foo going forward. So the system has to cope with it. So in V8, we had a choice. Either you have to always validate that there's no foo in the B prototype before you can execute the one up in A, or you have to put in a dependency system so that if somebody changes the B prototype, then it will invalidate the code you have already generated with these assumptions. The problem is that the B prototype is just an ordinary object, and you do not want to put in a general dependency system for normal objects. So in Dart, no, sorry, in JavaScript v8, we actually validate that there's no foo in the middle here before we execute foo in the A prototype. And that is expensive on the implementation side. Let me try to show you what it cost in generated code. So given the example we had on the previous slide, we now have a small benchmark. It's a micro benchmark. We don't like them, yes, but I'm trying to make a point here. It's a loop that just called b.foo repeatedly. And I warm up that program, and I look at what the various system generates. On the left side, you can see the result of what V8 generates. It generates nearly 300 bytes of comment code and 239 bytes of stop code. And the stop code is the source you need in order to support de-optimization if something goes wrong. Like, for instance, you add the extra code in the middle. On the Dart side, it's somewhat simpler. And you can see the optimized code here. It's much smaller. In fact, it's only a third of the V8 code being generated. So the simple semantics in the programming language just makes sense, right? It's much easier to make fast. Optimizing a little bit of code is much easier than optimizing a big piece of code. Generally less code is great, better memory performance. You also get predictable performance because you cannot change the code after you start it up. So keep it simple. It's good for us VM implementer.
And hopefully it's very good for application developers that get more predictable performance and generally just better performance. So let's benchmark this thing with a non-micro benchmarks benchmark suite. To benchmark the Dart VM, we've used multiple different benchmarks, but a couple of them that are interesting are Richards and Delta Blue that we know from the past are good predictors of how real object-oriented applications end up performing. That means that if we make Richards and Delta Blue faster, it actually will have an impact on a real web application. So using benchmarks that are sort of proven valuable in the context of other languages makes a lot of sense, especially if you want to try to bring a new programming language implementation to the web and make sure that it actually has some nice performance properties that match existing real languages. So we've used it in the past for Self, Strongtalk for tuning JVMs, and for V8. And now we're using these two benchmarks for tuning Dart. It's important to stress that these benchmarks really measure the performance of calling methods, memory allocation, and all the things that applications tend to spend a lot of time in. So Richards is an interesting benchmark. It's a kernel simulation benchmark that spends a lot of time in calling small methods and dispatching between different objects in here. What you see on the graph here is the Dart VM is on the graph, V8 is there, and Dart2JS, which is the generated code that we get from compiling the Richards version that's written in Dart to JavaScript with our own compiler and running that on V8. So you have three different runtime systems here in play that execute the same benchmark. So the Dart VM is the fastest, which is a nice thing. You can see that V8 performance is getting better, but not at the same pace as the Dart VM. Bigger is better here, by the way. V8 has tuned for this benchmark since its inception. We started out with the Richards benchmark, and we've achieved a lot of really cool speedups on these benchmarks over the years. We've tuned for like 6 or 7 years by now, and it means that V8 is fairly good at optimizing for this kind of application code and benchmark. Nevertheless, the Dart VM is already like 1.7 times faster than V8, generates way less code when running the benchmark, and it's just much better at executing that kind of code. The Dart2JS code is a little bit behind the handwritten version of JavaScript that we use to tune V8, and there are some extra checks going on in there, something we're improving over time, as you can see by the graph. But it's really nice to see that over the last year, we've been able to take the Dart VM from being a fairly simple implementation of a fairly simple language to being a really efficient implementation of a fairly simple language. This also shows on the Delta Blue benchmark numbers. Here the difference is even bigger. It's a factor of 2. Delta Blue is a one-way constraint solver, so it also spends a lot of time in allocating these objects, the constraints, and dispatching on them. Again, it's a benchmark that has been used for many different languages, and it's proven valuable in those contexts as well. It's great to see that, that here the same story repeats itself. The Dart VM is just a lot faster than V8, and of course it's also faster than the version of the Dart that we compile to JavaScript. It's kind of interesting to see that the Dart to JS numbers here are actually faster than the handwritten JavaScript. So the comparison here is between handwritten JavaScript that V8 executes, where we've tried to implement Delta Blue in a reasonable way in JavaScript, and then the generated code. This is also JavaScript that we compile from Dart code. And the reason why it's a little bit faster here is because we can do some analysis while compiling. We can do some inlining to help V8 execute this a little bit more quickly. We do expect us to be able to improve the quality of the Dart to JS compiler over time. And we're aiming for trying to be as fast as the code you would have written by hand in JavaScript. So, but clearly, the Dart VM is faster in this kind of thing. It's important to stress that performance is super important to us, and it really, really matters that you get a really scalable application platform out of using Dart. Having said that, I think it's important to point to the fact that users of Dart are really finding that in addition to getting good performance, they also feel that their productivity increase. Ali has written a really large font atlas generation tool, Glyph 3D, and it's written it in Dart, and he's been very happy with the productivity gains. And we get this feedback fairly consistently that people that use Dart for building larger things are very, very happy with it.
Thank you. Just to follow up on what Kasper said, performance is fantastic in Dart right now, and it's getting better over time. We've seen on the web the last few weeks some examples where Dart is actually outperforming Java. We're super excited about that, and we hope to get up to that level for almost all applications, basically. So the ultimate goal is to get the Dart VM into Chrome. I hope you all agree. Exactly. At least one. But we have a little bit of a problem here. I sort of mentioned that the garbage collection story with the DOM was a little bit complicated with all these reference counts and stuff like that. And putting Dart VM into the pit doesn't make it easier. And we cannot convince ourselves with reference counting that we can actually reclaim all unused cycles or memory data structures in the browser. That means memory leaks, and we really do not want that. So, so that's a problem. But we like to do something about it. And the only way we can make sure that we do something about it is to actually change the reference counted nature of the DOM. And we created a new project, started last month. It's called Oilpan. It makes sure that it handles garbage collection between the different segments inside Chrome and Blink, which is JavaScript, DOM, and eventually Dart. So we want to convert the reference-counted DOM into being traced. So we can trace through JavaScript objects, through DOM nodes, and through Dart nodes, and making sure we know what we have. The cool thing about tracing is you can find all pointers that points to an object. That means you can move the object if you choose to do so. You can even do serialization of the total web app, store it on disk, and read it in again, and start from that point on. And if we're really brave, we can start doing concurrent manipulation of the DOM. So we hope this is all appealing for you guys, because it basically means you get a much faster browser out of it, and a browser uses less memory. One thing about the concurrency is that when you have reference counting in the objects, you actually have to put in a lock around it if you do concurrent access. And that's expensive. Whenever you get a pointer to an object, you have to lock, increment the pointer, and then unlock again. So that's not practical when using reference counting. We can do all this if we unify the memory manager for Bling. So we're very excited about this project.
Yeah, so we feel like no presentation is really done without a demo of some sort. So lately, we've been working on making Dart even faster. No surprise there. A lot of modern CPUs today support what is known as SIMD, single instruction, multiple data instructions, where you have essentially instructions on the CPU that can operate on 4 floating point values in parallel, making it much, much faster. So the Dart VM has been enhanced with support for actually using those instructions. And no other web language has that support yet, so it's very nice to see this sort of in action in a browser, just making things faster. It's really useful for 3D calculations, image processing, audio processing, those kind of things. So we'd like to show you a little demo of Google Chrome with the Dart VM put in there, running a 3D animation thing with and without this SIMD support, just to show you the significance of this kind of work. So let's switch to the other.
5-ish. So here we're running inside Dartium, which is a build of Blink with a Dartium VM. And we have a bunch of monsters. They're all handled inside Dart. So that means that the animation, the skeleton positions, and all of that is happening inside Dart. It's not on the GPU. And this is the, somebody is beeping. This benchmark has been created, so it's trying to always have 60 frames per second, right? If it runs too fast, it will throw in more monsters, right? So it's trying to hit 60 frames per second, and we have now 34 monsters at play. We talked about this SIMD, we support it in the compiler, but we can turn it on with using a flag down here, so let's try it. SIMD. So this is using SIMD and animation in Dart. So a factor of 3.5 is not too bad, I guess. I'm really excited about this, and it actually gives you a lot more power to do computation inside JavaScript. So this is coming to you, and I'm excited. So let's conclude this presentation so we have time for some questions. So we're VM guys. We want to have a job moving forward, so we think that performance is always interesting. I hope you like that too. And we hope we have convinced you that if we really want to spark more performance into the browser, we need probably a different option than JavaScript. And I think Dart is one contender for that. The Dart VM is already faster than JavaScript and is approaching other programming languages out there. And again, just to point it out again, that higher performance is great for application developers. That's where you actually can get headroom to do more interesting stuff. Right now, the core Dart platform is stable. We have not sent out 1.0 yet. It will happen sort of late summer, so you can start using the SDK. That doesn't mean it's inside Chrome, but after we send out 1.0, that will be our main focus. Already now, you can see people on the web using Dart, and some of them have written fairly large bodies of code, and they're happy with it. And inside Google, people have started using it. There's critical projects start using Dart, and hopefully you'll see some of these applications coming to you soon. So this will conclude our presentation, and we should go to questions.
If we're unable to answer your questions right here, and there's a nice long line, if you go one back, please. We do have other Dart sessions here at Google I/O today. So if you found this inspiring and you want to see more on more specific details, here's a list of things in room, mostly in room 6, I guess, where you can go see other Dart presentations here. Yes?
All right, let's get the first question from the room.
Actually, my question is slightly related to that first one. Coming from a GWT development background, wondering if you've done any benchmarks and comparisons of the Dart to JavaScript compiler to the GWT's Java to JavaScript compiler.
I don't have any numbers to share with you there. It's easy to try out, by the way, because, for instance, Richards and Delta Blue, they're all available in Java, so you can try it out yourself. I hope they're doing great on it, by the way. One thing that I would like to say is that we are trying to go beyond Grid in that we are doing a native Dart VM that can boost performance and reduce startup time. This is really what we want to get at, especially for mobile platforms where loading an application can be a dog and take many resources, right? Mm-hmm. Faster VMs, faster startup means less battery. Next question, please.
Hi. Have there been discussions of including Dart in other browsers? And if not, would it be possible to add it through plugins? And
it would be fantastic to have all browsers using Dart. Clearly, people have strong opinions when it comes to programming language. I don't really understand why, but that's how it is. I just want to make sure that people have the right tools to build the applications with. Our system is completely open source. It has a well-defined API, so when other browsers think that this extra boost of performance will be good for them, they can take it up, and we'll be happy to help them out, basically. So we are open for collaboration.
We have a few questions from our online audience, and maybe just try to answer a few of them as well. I can cover the second one. I think you covered the GWT question already. This question is about Android Studio, and if we're planning on releasing something similar for Dart. In a sense, we already are releasing something similar for Dart. We have a fully featured Dart editor, but in addition to that, and maybe this is what the question is really about, we do have support for using and working with Dart from IntelliJ. And the JetBrains team is here, and if you're interested in this kind of thing, you definitely come talk to them at the booth. So the short answer is really that we're looking into releasing all sorts of nice tools for Dart, being based both on Eclipse and IntelliJ, definitely.
Let's take the next question from the audience here.
Hi. I have a bit of seemingly long-standing wisdom that I'd gotten a few years ago that occurs to me might be out of date, which is the idea, this is about V8, that JavaScript objects are going to be more performant if you define prototypes rather than defining methods dynamically in a constructor. And it occurs to me that with hidden classes, perhaps you guys have optimized it so that it wouldn't make a difference.
Well, we certainly tried to, what we do, we tried very hard to optimize in V8. But it's still the case that you have to create a new class whenever you add a property in a way you haven't seen before. So you get a forest of classes, even for the same constructor. And in Dart, right, you know, you only have one format for one class, whereas in V8, right, depending on how you add properties to an object from a given constructor, you can get a sea of them. And we have to cut off at some point, so we have limits inside the V8. Now, when you have reached a certain number of hidden classes for a constructor, we say we actually just, we de-optimize now, and we make sure that objects will only be treated as maps and get slow.
So is it true that then prototypes would be more performant in V8 than using defining properties, even if you define them the same way every time in a constructor?
I think it depends on exactly the same the setup. You can make it so they perform exactly the same. It really depends on how the application adds properties to your object on the fly.
A little bit of extra information there is that V8 does try to move functions to the class side, so to share them behind the scenes anyway. So you could say that adding on the objects is sort of optimized too, but I think it really depends on your application if it makes a difference.
Next question.
One of the arguments for Node.js is that you have JavaScript everywhere, server-side even. Are you looking at Dart server-side, or is there more momentum behind Go?
That's a great question. But of course we have that. So we have a server-side library you can use, and you can use the Dart VM standalone if you want to. And you can use the same kind of asynchronous programming style as you do in Node.js. In fact, you saw the performance numbers on the slide. This is a performance measurement system we are using internally. It's all written in Dart, and it controls a lot of machines at the same time. We use exactly that server-side system. So yes, we have libraries for supporting server-side Dart execution. But our main focus right now is the client side and getting it to Chrome.
So I think we have time for one more question, but if you have more questions, that you guys in the line, Lars and I will be at the office hours booth, so come to us and ask those questions there. But let's take the final question.
Yeah, my question is like, there's a lot of JavaScript code already there, so is there a tool, or even if it's possible, to convert JavaScript into Dart?
So generally, we find that people that try to rewrite existing code bases from JavaScript or from other languages to Dart are generally fairly successful. It's also possible to use the JavaScript code from Dart by wrapping it a little bit and using what we call JavaScript interop. But generally, translating from JavaScript, unless you use very, very dynamic features of JavaScript a lot, it's actually reasonably easy, and a lot of people have good success with that.
So you guys have a tool?
There is no tool for that, no.
Thanks.
Thank you very much.